So our last section in chapter 2 is 2.5. Okay, it's on solving higher order inequalities. So as I said, things that are not just linear, but maybe quadratic or cubic. We're going to do a couple different methods. Algebraic methods are only going to work if we can factor. Okay, so the method I'm going to teach you is dependent on that happening. If we come across problems we can't factor, then we'll stick with using the graphing calculator. All right, so one of the equations we looked at either earlier, I think it was earlier in chapter 2, had to do with projectile motion. Okay, so if you already have this, you don't need to write it again. It's the same equation. Okay, negative 16t squared plus v sub 0t plus s sub 0. And what this, again, does for you is it tells you the height of your object as a function of time. Okay? This formula assumes that you're using feet for your distance and seconds for your time. Okay, so we'll always stick with those units in this class, feet and seconds. V sub 0 is your initial speed of the object, how fast when you released it or threw it or launched it, whatever you did, how fast was it going? And S sub 0 was the initial height of the object. Okay, if it says an object was released from ground level, that means the initial height would be 0. Yep. Okay, so now what we can do is, instead of just asking a question, thinking of this as an equation, like where does my object hit exactly 50 feet high? Now I could say something like, when is my object at least 50 feet high? Okay, so that would be, when is my object greater than or equal to 50 feet? Okay, so now we can put an inequality in that equation and answer questions like that. Okay. So in this example, we'll use the graphing calculator. Okay, and it says we're going to throw a ball straight up in the air. And you might think, well, if you throw something straight up, that's not projectile motion. It's the same thing. Whether you throw something straight up or you throw it at an angle and it kind of arcs, it's really the same formula to figure it out. Okay, so this ball is going straight up in the air with a speed of 80 feet per second. Okay, now I don't want to know when the ball hits 64 feet. I want to know when it's at least 64 feet above the ground. Okay, so that means 64 feet or greater. All right, so let's take our equation up above. We'll turn it into an inequality. Okay, just decide if we need a greater than or equal to or a less than or equal to. And we'll fill in any information they give us. All right, so I want to know when the height is at least 64 feet. What letter in that formula represents my height? David?
S.
S. So I want to know when S is greater than or equal to, okay, when my height is greater than or equal to. And now I'm going to fill in. Okay, hold off on that for 1 second. Negative 16t squared plus 80t. And it's being launched from ground level. So that tells me my initial height is 0. Okay. So what I'm looking for is this. Okay. I want to know when the height is greater than or equal to 64. Okay. Any questions on that? Right, so that's how my height is figured out. Okay, that's my formula, and I want to know when this right here is greater than or equal to 64. Okay, so if you wanted to write it as an inequality, this is how you do it. When is the height of my object, which is modeled by what's in that box, greater than or equal to 64? Okay, so how would I use the calculator to figure that out? What do I have to do first? Yeah, man.
Did you plug in the equation on the left?
Yep, plug in this expression on the left. So negative 16x squared plus 80x. All right, and now what?
And then in the second line, you would put 64.
Yep, put 64 on the second one. Now, let's check our window, make sure we've got values that make sense. So x is time. What kind of values make sense for time here? Yep, positives. Okay. After a certain point, though, the object is going to be back on the ground. Okay, so we don't know when it's going to hit the ground, but really we don't want to look at anything that's below the ground. Okay, so your y min should really be 0. Your y max is how high the object is going to go. We don't know how high it's going to go at this point, but let's just guess it goes 80 feet high, and if the parabola goes off the screen, we'll just adjust it. Yes, okay. So, it looks like our parabola is going, oh, that should be a plus 80. Let me check it again.
There we go.
That looks a little better, but I think it's still going a little higher than what we've got. So let's,
100. Yeah, 100.
100 works?
Yeah.
All right, so it goes a little higher than I thought.
Oh, right there.
Just barely. All right, so we've got our parabola. Okay, that models the object, and we want to know when it's above 64 feet. So what do I need to do? What do I need to do next? Yeah, go ahead.
Find where the parabola intersects our line.
Yeah, so as Josh just said, find where the parabola intersects that line. Get those 2 points. Find the x values. And that's where I'm above 64 feet. Okay, so I'm going to go second calc, intersect. Okay, I'm going to do the one on the right if somebody else has their calculator and can do the one on the left. Okay, so this is where the guess is important, because the one you're closer to will give you the one you're looking for. All right, so the maximum time is 4 seconds. And was it greater than? Yeah. When is the ball at least 64 feet? So that's 64 or higher. Okay, so my time goes from 4 seconds to, did anybody get the other intersection?
That's 1.
1. Thank you. Okay, so between 1 and 4 seconds, the object will be above 64 feet. Okay, any questions on how we figured out the time? All right, so now let's figure out, using algebra, bless you, how long the ball stays in the air. Okay, what does that mean? How long the ball stays in the air? What's something we can try to tie into this equation? Something about height. The ball is in the air, and it's going to be an inequality. Yep, Josh?
Whenever the height is greater than 0.
Yeah, whenever your height is greater. Now, the book did greater than or equal. I think technically if your height equals 0, you're back on the ground, but that's the way the book did it. But I'm going to do strictly greater than. Okay, so here's my height, negative 16t squared plus 80t. And I want to know when that height is greater than 0. Because as long as the height is greater than 0, the object must be in the air. Now we'll solve that. Does anybody see on the left-hand side anything that's common to both terms? Yep, t and anything else? T and what else? 8. Yeah, 8 is common. How about something even bigger? 16. In fact, what I'm going to do is factor out, just because I like my squared term positive, I'm going to factor out a negative 16t. So negative 16t. And what would be left in parentheses? I might have to adjust something. Yeah, t minus 5. Yeah. Okay, so if you factor out a negative 16t, you're left with negative 16t times t minus 5 is greater than 0. Okay, so you've got two different factors here. You've got this one, and you've got this one. I want to know when the product of these two things is greater than 0. Okay, any thoughts here about that? Anybody think how we can start to figure this out? Okay, look at what we have here. Yeah?
When you said which equation greater to 0, so negative 16 is greater than 0, and 2 minus 1 is greater than 0.
Okay, trying to doing it like it's equal to 0. Well, basically, but we don't even have to do that much. Because something here doesn't really, it's not really going to ever help us be greater than 0. Which factor there is never greater than 0? Nope, not the t minus 5. Why can negative 16t, why will that never be greater than 0? How come this is always going to be negative? Always. Yeah?
Because it's a negative number and time can't be negative, so if you tried to multiply it, would never be a positive number.
Right, you're always going to have a positive times a negative, which is always going to be a negative. So now we know this box in blue is always negative. So now this box in green, what sign does it have to be so that we get something greater than 0? A positive number greater than 5.
It's going to be negative. Negative times negative is positive.
Right. This has to be negative. Okay, what's inside that green box, it's got to be negative. If it's not, you'd have a negative times a positive, and that's not greater than 0. Okay, you can't control this first box. It's going to be negative. So somehow make this second box negative, and that will tell you where the product of the two is greater than 0. Okay? Any questions why t minus 5 has to be negative? Okay, so when is t minus 5 negative?
Yeah, you already knew the answer.
Anything that's more than 5? Yeah, less than 5. Okay, so the question is, when is this less than 0? When does it come out negative? Okay, as long as t is less than 5, which means our object is in the air less than 5 seconds. It's in the air exactly like 4.9 repeating seconds. When it hits 5 seconds, the object is back on the ground. Okay, so any questions on that? So it requires being a little bit clever and just recognizing that something's always negative times another negative will give you a positive, okay, greater than 0. Okay, and that's the idea we're going to kind of look at when we do what's called a sign chart or a sign pattern. Okay, so we'll look at that in just a little bit. All right, and when is the ball at least 64 feet off the ground? We did that graphically. We could do the same thing algebraically. You could turn it into a quadratic, okay, equation and plug into the quadratic formula and solve for the two values that we had. Okay. Any questions on this algebraically? You just have to use the quadratic formula. Okay, if not, I think we'll just stick with doing it graphically. Okay, that's fine. Because we're going to do a lot of stuff without the calculator in a minute, so we don't need to spend too much more time on that right now. All right, so one way you could do the question that we just skipped, okay, and we can come back to it if we want, is with what's called a sign pattern. Okay, when we use a sign pattern, the whole goal is you're going to try to factor. And when you factor something, okay, every linear factor is equal to 0 at exactly one value. Okay, so for example, I take this, x squared plus 3x plus 2, and I factor it into x plus 1, x plus 2. Those are linear factors, and each one of them has exactly one value you could plug in and get 0. The top one is -1, the one below it, -2. Okay. Any question on that idea? Okay, so for that top one, okay, x plus 1. -1 is kind of it's like the division line. Okay, if you pick numbers on one side of -1 and plug them into this, you're going to get either positives or negatives. If you pick numbers on the other side of -1 and plug them in, you'll get the other thing, either the positive or the negative. Okay, so -1 is the division line between when you plug stuff in, are you going to get a positive answer or are you going to get a negative answer? Right, so here's another example, just like I did up above. If you had the factor t minus 1, if you plug in 1, you get 0. If you plug in numbers bigger than 1, you're going to get a certain sign. If you plug in numbers less than 1, you're going to get the opposite sign. Okay, for t plus 4, -4 is what makes this factor 0. Plug in numbers bigger than -4, something's going to happen. Smaller than -4, you're going to get the opposite. Specifically in this case, bigger than -4, you get positives. Smaller than -4, the answer would come out negative. Okay, any question on that idea? That's really the whole thing behind a sign pattern. Okay, so what we'll do is we'll make a number line for each factor. Okay, some problems will only have 2 factors, some might even have 3. Okay, it depends. And on the number line, we're going to mark the number that makes the factor 0. So in this case, like t minus 1, we'd mark 1 on the number line. Okay, just like this. In this one, we'd mark -4. And then we're going to determine the sign in each section of the number line. Okay, when you put that number on, you broke your number line into 2 pieces. Things to the left of it, things to the right. In this top one, if you plug in things to the left of 1, you get negatives. Okay, so any number that's below 1, you plug it into t minus 1, your answer will be negative. If you pick any number above 1 and plug it into t minus 1, you get positives. Okay, same thing here. Any number below -4, plug it in, you'll get a negative. Any number above -4, plug it in, you get a positive. Okay, so we're kind of separating that number line into 2 sections. Okay, and page 113 shows you exactly what I just drew in blue on the side. Okay, any questions so far on the sign pattern? So just looking by sign pattern, I just mean, is it negative or is it positive? That's what we're trying to figure out. Okay, and then I'll come back to this in a second. Okay, so you can leave a little space, but I want to do the first part of what I just explained to you. And then once we do that, we'll come back and combine everything to make a final picture and get our answer. Okay, so just leave a little space and we can copy that down in a second. All right, so as I said, this depends on being able to factor. If you can't factor, you can't use this method. All right, so we're going to try to factor what's on the left-hand side. And it's already greater than 0, okay, which is good. If you don't have 0 on the right-hand side, this method doesn't work. Okay, so just like when you work with any quadratic, if you're going to factor it or use quadratic formula, you've got to get everything on one side, 0 on the other. All right, so I know that's going to factor as 2x and x. How about my signs? Let's see. Yeah, Quinn?
Plus and minus.
All right, we're going to need a plus and a minus. And where do you want to put the plus?
In the first box. First parentheses after the 2x.
I would put it in the second, I think. Just because I'm looking at this plus 9. So I know I want to put a number here that when I multiply by 2, I get a pretty big positive number. Okay? So let's try minus and plus. And what times what gives me 5? Yep, Al.
1 and 5.
And I'll try it in the order she said. So we've got 2 times 5 is positive 10x. Take away 1 gives me 9. Okay, so we factored it. Any questions on the factor? All right, so now next thing I want to do is drew my number line, mark the zeros. Okay. 2x minus 1. What would be the value you plug in for x here and get 0? Yeah?
1 half.
1/2. And what would be the value here that you plug in and get 0? What is it? Yeah, -5. It doesn't have to be exact, just roughly on the number line. And now I want to separate it into the 2 regions, positives and negatives. All right, let's start with the 1/2. If you pick numbers bigger than 1/2, like 5, okay, anything bigger than 1/2, and you plug it into this, will your answer be positive or negative? Positive. If you plug numbers in smaller than 1/2, like 0, what kind of answer do you get? Negative. Okay, so one side is always negative, the other side always positive. That's how it always works. How about -5? If you plug in numbers bigger than -5, like 0, what do you get? Positives. How about numbers smaller than -5? Negatives. Usually that's how it works, negative, positive. The only way that could be flipped around is if they did something like this. If you put a negative in front of the x, now that's gonna change things a little bit. But don't worry about that for this one. All right, so now we've got our number lines, okay, for each factor. Now we're going to combine them into one big number line. Okay, so now I'm going to create a number line for both of them at the same time. I'm going to mark both roots on the number line. -5, 1/2. How many regions do I have to look at in this number line? 3 regions. Okay? I have to figure out where things are negative and positive in each region. Okay? And why do I want to do that? Because that'll answer this question. If I can figure out where things are greater than 0 or positive, that's the answer to this question. Where are things greater than 0? Where are they positive? Right, so now I just have to figure out which of these 3 sections are positive. Okay, so we're multiplying the 2 factors together. Okay, let's look at what happens when we're less than -5 in both of them. Okay, in the first one, if you are less, say -5 is probably over here somewhere. If you're less than -5, what kind of number do you get? Okay, I'm just going to write that off to the side, negative. And if you're less than -5 in the other one? Another negative. And what's a negative times a negative? A negative times a negative in this region gives me a positive. Okay, now we're going to look at what happens when we're between -5 and 1/2. Okay. In the first one, if you're between -5.5, what kind of number do you get? Negative. How about between -5 and 1/2? Now you're getting a positive. And you're going to multiply together a negative times a positive, and that gives you, that's a negative. In the last section, we are greater than 1/2 in both. Okay? Greater than 1/2 gives me positive. Greater than 1/2 gives me, and what's a positive times a positive? Positive. So now I know exactly where this thing is above 0 and where it's below 0. That's the answer I'm looking for. Where was this thing greater than 0? Okay, these two regions. Right, so how would you write the answer for this region? All numbers below -5. How do we write that, Amanda?
Wouldn't it be parenthesis, negative infinity, comma, -5 bracket?
If in this case we are not including
Oh,
0, it has to be strictly positive. So,
that would be parenthesis.
yep, so we just have to put a parenthesis.
And then the new thing.
Yep.
And then 1/2, comma, infinity, parenthesis.
Yep. So if you pick any number in this interval, I guarantee you the result will come out positive. If you pick a number between -5 and 1/2, it will come out negative. Okay, so that's the sign pattern. Okay, you have to factor it, look at whether it's positive or negative in each region, and then combine it all together to make a final picture. Okay, so let's try this one. This might be a little trickier if you had to factor it because it factors into 3 things, not just 2. So let's look at each one of them, find the value that makes each one of them 0, and then determine the behavior to the left and to the right of each one. Okay, what value would you plug into the first factor to make it 0? Yep, John? 0. How about the second factor? Yep.
-3.
-3. And the last one would be +1. Okay, now determine the behavior in each section. Okay, for my first factor, numbers less than 0, plugging them in will give me a result of negative. Greater than 0 will give me a result of positive. Second factor, plug in numbers smaller than -3. What's the result? Oh, Caleb?
Negative.
Yep, negative. And Grayson, how about you plug in numbers bigger than -3? Yep, you get positive. And the same behavior here. Plug in numbers smaller than 1 for x, you get negatives. Plug in numbers bigger than 1 for x, positive. So now we're going to put all that together on one number line. Okay, how many regions is this final number line going to have? It's going to have 4 regions. It's going to have numbers less than -3, between -3 and 0, between 0 and 1, and from 1 on to infinity. Okay, so let's check less than -3 in all 3. Okay, in the first one, if you are less than -3, what kind of numbers do you get? Yep, so we get a negative. How about less than -3 in the second one? That's a negative. And less than -3 in the third one? Negative. So you'd have a negative times a negative times a negative. What's that? So that's a negative. You can just make the negative symbol, or if you want to write negative, that's fine. Okay, let's check the second one. Then you might start to notice a pattern. Okay, between -3 and 0. Okay, so x, between -3 and 0, negative. Okay, second one, between -3 and 0, positive. And between -3 and 0, negative. What's a negative times a positive times a negative? Positive. Does anybody notice the pattern in the final chart, final sign chart. Yeah?
Negative, positive, negative, positive.
Yeah, it always alternates. Negative, positive, or positive, negative. Whatever it starts on, it just alternates. So this section will be negative, this section will be positive. Okay, if you're not sure, go through it and you'll see that that's what happens. Okay, this one wanted to know where we are greater than or equal to 0. Okay. Well, in that section we have positives, and in that section. What's going to be the difference about how I write my intervals in this problem versus the last one? A little change there. Yep, Molly?
It can also be equal to.
Right, it doesn't have to just be positive. It can also equal 0. Okay, so that means I'm going to use what symbol? On my bounded interval parts, I'm going to use a bracket. Okay, so between -3 and 0, or where else am I positive? Or where else am I 0 or positive? Yep.
1 and up.
1 to infinity. Okay, and what's nice is you can always confirm this with a calculator if you need to. Okay, you can just graph this. You don't even need to factor it to graph it. And you can check on the screen and see if that's true. Great. So any questions on that sign chart? Okay, again, you've got to be able to factor it. If you can't, this method doesn't work. Any questions how you would do this one? It's the same rules when you divide positives and negatives. Positive over positive is positive, negative over negative, positive. You do the exact same steps, except you're dividing instead of multiplying. Okay, but doesn't change anything. So any questions on that one? Let's just make sure we know the roots. What's the root of the numerator? 4, and the root of the denominator?
Negative 2.5.
Yeah, negative 2.5 or negative 5 halves. Yeah. Okay, so no questions on that one? All right. So if you cannot factor the expression, you can't use the sign chart method, then we'll graph it. Okay, and this will be the last thing in 2.5. I have 2 methods I can use graphically to solve this. What's one method I could use? About Andrew? What's one method I could use to solve this?
Plug in everything on the left.
Would you say do what with?
Put first, you get x on the same side.
Okay, you could get all the x's on the same side and all the numbers. You could get everything on the same side. And then what would you have on the other side if you did that?
Just a 7, 1. So
How about the other side, though? Because if you move everything that's there to the left, what's going to be on the right?
0.
Yeah, so basically we're getting the 0 by itself on one side. That's one way you could do it. Or what's the other way we could do it? If we don't want to rearrange anything. Yeah.
Could you just put like the left side in y1 and the right side in y2?
Yeah.
And see where they
And see where they what?
are like above 0 or when they cross.
Not if we do y1 and y2. We're not going to be looking for where they're above 0, because we won't be plugging in a 0.
But it could be where they cross.
Yeah, we'd be looking for an intersection. Okay, so we can do it either way. Okay, let's just leave it like it is. We'll do it as an intersection. Okay, so we'll plug in x cubed minus 2x squared minus 5x plus 7. And I'm going to be looking for where that is greater than or equal to 2x minus 1. Okay, so where is the thing in blue above the thing in red? That's what I'm looking for.
It's not going to work. Get x plus 1.
Oh, did I put the wrong? Thank you. Well, here's the thing in blue. Well, we could answer that question, but that's not the question I asked. So 2x plus 1. Thank you. Bless you. Okay, so there's our cubic. And I want to know where that is above the thing in red. Okay. How many, in how many places is the thing in blue above the thing in red? Two, right? It's above it from here to here. And where else?
Like the edge of the curve.
Yeah, and from here on forever. Okay, that's where it's above it. So I'd have to find this intersection, and that intersection. Okay, does anybody want me to go through finding all three intersections? All right, so let's just call this one A, comma, B. We'll call this one C, comma, D. It has some coordinate. And this one E, comma, F. Bless you. When I write my interval, does the interval use the x values or the y values? X, right? Because that's what the problem is about. We're looking for x values. So what x values here is the blue graph above the red graph? From what to what? Yeah.
A to C.
From A to C. Okay, whatever those are, you'd have to find them. Bracket or parenthesis on that?
Bracket.
Bracket, yep, because we have the equal to. So between A and C, and what other x values? Amanda?
E to infinity.
From E on to infinity. Okay, so again, just find those intersection points and then plug them in, and that's your answer. Okay, any questions on that one? Okay, so that's the approach you can take, one of the approaches you can take if you can't factor it. If you don't like intersects, bring everything to one side and do a root. But then the only danger there is if you make a mistake bringing everything to one side with arithmetic, then it's going to come out wrong. Of course, you could make a mistake like I did, just leaving it the way it is too. So just be careful when you type it in. All right, so last thing we'll look at, we've already talked a little bit about, and that's graphs of polynomial functions. Okay, polynomial functions are pretty nice to draw, pretty nice to work with, because they don't do anything weird. All right, they just take twists and turns. You can plug in any number you want to a polynomial. The domain is always all real numbers, because you don't have square roots in polynomials, and you never have fractions, okay, with variables in the bottom. Okay, so you never have to worry about domain with polynomial functions. And the other thing is the graphs are always nice and connected. Okay? You can get from any point to any point on a polynomial without ever picking up your pencil. You can't do that with all graphs. Okay? We've seen some graphs that are in separate pieces. Okay? Not polynomials. They're always nice and connected. Okay? And that's the general form of a polynomial. Okay? You have a leading term, okay? And then your next term, usually it's one exponent lower. And then after that, we put the next exponent lower, until finally we get down to just having an exponent of 1 and then the constant. Now, sometimes you have a polynomial that doesn't have every term in it. Okay? You could have something like this. There's no x squared term and there's no x term in that case. Okay? Just the leading term and just the constant. Okay? Your exponents in polynomials always have to be non-negative integers. And because of that, that's what causes you to never have x's in the denominator of a fraction. Okay, so you'll never have to worry about dividing by 0. Okay, and this basically just, so probably a new symbol we haven't seen, that means for all, or for every. So what this says is for every value of n, okay, a sub n, which are the coefficients, are real numbers. Okay? So this just says all your coefficients in the polynomial have to be real numbers. You don't have imaginary numbers in a polynomial. So if you want to write it out in words, you can write that. Okay? Every coefficient in a polynomial is a real number. That's just a lot longer to write than this. Okay? And as long as your first coefficient is not 0, okay, this is called the degree of the polynomial. Okay? Because we always write it with the highest exponent first and then going down. That's descending. And as long as you don't make this a 0, that n right there is the degree. Okay? And the degree tells you a lot of different things. How many turns it can take, which is related to how many times it crosses the x-axis. Okay, so we have some names for some special ones. If you have a polynomial that's a degree 1, okay, like y equals 2x plus 4. What's a degree 1 polynomial? Anybody know what it looks like? Yeah, yeah, it's linear. It's just a line. Okay, how about a degree 2 polynomial? Like x squared plus 7. What's a degree 2 look like? Or if you don't know what it looks like, you could also tell me the name, which begins with a Q. Yeah,
It's quadratic.
yeah, it's a parabola or a quadratic. And degree 3 is a cubic. Anybody know what degree 4 is called? A quartic, yeah. So we don't really use, these are the 3 we use a lot. Usually if it's above that, we just say it's a polynomial of degree 6, 12, okay, whatever it is. Okay, and as I said earlier, the domain of a polynomial is all real numbers for every single polynomial. The range depends. Okay, think about the range of a parabola versus the range of a line. They're different. Okay, parabolas don't go up and down forever. Lines do, as long as they're not horizontal. Okay, so range still depends, but domain, super easy with a polynomial. It's always all real numbers. All right, so we've spent a little bit of time already looking at cubic functions, so I'm not going to spend super long on this. But basically, those are the shapes you can get for cubic functions. Okay? Cubic functions can turn up to 2 times, and they can cross the x-axis up to 3. And notice I say up to. Okay? Just because it's a cubic, it doesn't necessarily mean it's going to cross the x-axis 3 times. Okay? The first 2 are examples of cubics that would only cross the x-axis once. All right, so 4th degree polynomials. We haven't really spent any time with those. How many times do you think a 4th degree polynomial can cross the x-axis at most? Yeah, Zach?
4 times.
4 times. How many turns do you think it can take at most? 3. Yeah. Okay, so there's your 4th degree polynomial. Not every 4th degree polynomial has to have every single term from the cube, the squared, the linear, and the constant. This is a 4th degree polynomial. It's the simplest one you can have. And because it's so simple, it actually doesn't do anything very interesting. It almost looks just like a parabola. But when you start adding in these other terms, that's where you can get more twists and turns. So basically, you can get a W shape. Okay? Sometimes it can be more or less extreme. It could be a symmetrical kind of W, or it could be one that's just a very little turn. Okay, but you can get that, or you can get that behavior flipped. Okay, you could get something that really just looks like this. That's what y equals x to the 4th would be. It looked like a parabola, but a little flatter on the bottom. But the important thing is if you look at the ends of the polynomial, they either are always both going up or they're both going down. And that's going to be true anytime you have an even number right here. Okay, but we'll mention that, and I'll make a little chart so you can tell. All right, so let's graph that and find the domain and range. Okay, so x to the 4th plus 5x cubed plus 2x squared minus 8x plus 1. And I just cleared it. So let's type it in again. X to the 4th plus 5x cubed plus 2x squared minus 8x plus 1. Graph. All right, so I'm looking for domain and range. Okay, the first question shouldn't require too much thought. What's the domain? All real numbers. You can raise anything you want to the 4th power, anything you want to the 3rd power, and multiply it by 5. You're never dividing by 0. You're never taking a square root. Okay, so domain, all reals. Okay, range. Does this graph go up forever and down forever? What do you think? Yeah?
Well, not down forever.
No, not down forever. I can't quite see where it stops, but I have a feeling if I just go a little lower, I'll probably be able to see. Okay, so it does go up forever, and it's always connected. Okay, you could draw this without ever picking up your pencil. But it does have a minimum, okay, right there. How can I find that lowest value in the range? And one way to do it is with calculus, but we don't have that yet. So how can I do it on here? Yep. Yeah, and then what do you want to do from there? Yeah, minimum. Okay, so just go over to your minimum, pick a point to the left, to the right, take your guess, and this has a minimum y value of negative 11.95. Okay, and it does reach that value right where I am. So the range is negative 11.95 and up. It goes up forever. Okay, questions on the domain or range? All right, so you can look at the graphs of 5th degree polynomials. It's just extending what we already know. 5th degree polynomials can cross the x-axis 5 times. They can take up to 4 turns. So here's an example of a 5th that does every turn it can. 1, 2, 3, 4, 5. And of course, if you put your x-axis in, there's your 5 times it's crossing. Okay, so notice when I drew all those twists and turns, okay, you have what's called local minimums and maximums. Okay, I'm not saying that this is the lowest that the function ever goes, right there, but I'm saying in the surrounding area, it is a low point. Same thing here. A local max doesn't mean that it's the highest value in the function. Okay, this goes up forever. There is no global max. But in the surrounding area, this is the highest point. Okay? So any questions on the difference between a local minimum or maximum and a global minimum or maximum? Okay, global means it is absolutely the highest or lowest point, and there is nothing higher or lower. We found a global minimum in this one. There is nothing lower than that point. Okay? There's a local minimum right in there. There's a local maximum right in there. Okay? So if you need to write that, you can, or if you understand, a local max is just a point that's higher than everything else around it. A local minimum is a point that's lower than everything else around it. Okay, and together, your local mins and maxes are called local extrema. So if you see a problem that says find all local extrema, that just means find all the local minimums and maximums. And technically, I guess you could say that a global minimum is also a local minimum, but not the other way around. So technically, if you just want to say, all right, I'm going to focus on this area, that's a local minimum in this region. It also happens to be a global minimum if you look at the whole graph. Any questions on that? All right, so when we have a graph that takes these twists and turns, a lot of times we just use the calculator and we figure out mins and maxes with that. Okay, it's very, very simple to do with calculus, but it's just not something we're going to learn this year. Right, so I'm going to graph. Does everybody have what's on the left? Okay. Let's graph x cubed minus 4x, and we'll find the local minimum. X cubed minus 4x. Okay, this is pretty clear. I don't think we need to change our window. Right, we've got a local min right there. Okay, so they want me to find what the minimum is and where it occurs. Where it occurs is the x value. What is it is the y value. Okay, so just make sure you're clear on that, especially for the test. Okay, so we're going to calculate a minimum. So pick a point left, right, do my guess. Okay, where does the minimum occur? 1.15. Okay, what is it? That's my y value, negative 3.08. And you do the same thing for the maximum. You just do second calc maximum. Don't assume that it's symmetrical. Like if it was negative 3.08, it's positive 3.08. It could be, but I would just calculate it and double check it. Any questions on how you'd find a local max? Okay. Keep in mind, too, if you don't see all the twists and turns that the graph is taking, that means there could be something off the screen. Okay, so I've had problems like this on a test before, where you have a graph that does something like this, and people are looking only in this box. So they say, yep, there's one local min, one local max. And then I say, well, did you zoom out? And then when they zoom out, they find another local min and another local max. So be careful if something's off the screen. Okay, you need to check that. All right. This one, I think I'm gonna skip over. Okay, because it's just a projectile motion problem with an initial height of 200 feet and an initial velocity of 64 feet per second. When you graph it, basically it's going to look something like this. You're throwing an object off a building. Your parabola will look like this. That'll be your axes right there. And it's basically going to go off the building. And they want to know when it reaches a maximum height. So when you graph it, you just do second calc maximum. That one shouldn't be too hard, as long as you know the formula for projectile motion. All right, so the last thing we're going to look at, which is really tied in with local mins and maxes, is where a function increases and decreases. Okay, another thing that you'll do in calculus. Okay, where is this function increasing? We don't have any numbers, just as letters. Amanda? From B to C. Yep. So this is increasing from B to C. Right at B and C, it's not doing anything. And in fact, if you look at the slope of this curve, does anybody see what the slope of the curve would be right at point B or point C? If you drew a line tangent to the curve right at that point? It would be 0. And that's where calculus comes in. We know that anytime a function goes from increasing or decreasing to increasing, at some point you had to be perfectly flat as you took the turn. Wherever you're flat, your slope is 0. Knowing that, you can find the mins and maxes without a graphing calculator. You just have to know the slope is 0 at that particular point. Okay, so it's increasing from B to C. Where is it decreasing? From, what about Taylor? From where to where?
A to B.
Yep, A to B, it's decreasing. And where else?
C to D.
Yeah, also from C to D. Okay, so as a function goes from increasing to decreasing, what happens? What is created when you do that? If you go from increasing to decreasing? Something we just talked about is automatically kind of created. So what happens if I went like that? I went from increasing to decreasing. Okay. I did make a curve. That's also a curve that doesn't have what I said, because I didn't go from increasing to decreasing. That was just always decreasing. Something special happens when you go from increasing to decreasing.
You said it goes like flat.
It goes flat here, and what's happening, right? What is this right here? Yeah?
A local maximum.
Yeah. You create a local max. Or it could be global. It depends. Create local. At a minimum, it's local. Could be global. Max. How about if you have a function that goes from decreasing to increasing? Right in there. What did you just create there? Yeah? Yeah. So anytime you go from decreasing to increasing on a connected on a polynomial, you just created at least a local minimum, maybe even a global minimum. Yeah, I think that's... Okay, and if we want to be more specific about what does it really mean if a function is increasing or decreasing? A function is increasing if as x goes up, y goes up. Okay, that's what increasing means. That's what the top one says. Increasing means as x goes up, y goes up. Decreasing means as x goes up, y does what? Oh, Jeff?
Y goes down?
Yeah. So for a function decreasing, the values of y go down as x goes up. Okay, that's what increasing and decreasing means. Okay, so if I gave you, actually that's the same problem we already did before. Find where that function is increasing and decreasing. Okay, it looks something like, let me just copy it. Put it over here. Okay, I wanted to figure out where is that function increasing and decreasing. I've got to find the local mins and maxes. Find this. Find that. And then I would say it's increasing up to the first point and from the second point on. Okay, where is it decreasing? Between the 2 points. Okay, so when you write where it's decreasing, you'd need one interval. Where it's increasing, you need 2. connected with union. Okay, so any questions on that? All right, so a lot of different things here that really help us all year, knowing the behavior of polynomials and how many twists and turns they can take. That's pretty important. Okay, that helps you to know, are you looking at everything on the screen that you should be? All right, so the homework, it's mostly just individual problems. It's not one big set because we usually do a lot of little things, so I just try to do like 1 or 2 problems of each thing we do. Okay, so on page 116, okay, it's 1, 3, 4, 16, 20, 22, 28 through 30, and then 49 to 51, I think, is one problem. You have to do each part to do the next. Okay, and then on 149, 1, 3, 9, 10, 16 to 20, just the evens. Okay, don't do all, just evens. And then 25, 29, 38, and 39. Okay, so we'll look at that tomorrow. We'll review it. Also talk about what's going to be on the test tomorrow on Friday. And progress reports come out on Friday. So make sure you come see me if you have to make anything up.